Well, thank you for coming again and not stopping your physical chemistry on last time meeting. So, who we are and what are we doing? So, I believe it is still a physical chemistry class. And where did we stop last time? On coming here and getting general ideas what are the objectives of the class, which would be something like getting principles for electrons and ions moving in molecules and staying together for stability and physical properties. And the motion of electrons doesn't follow our intuitive expectations from macroscopic world. Therefore, we need to look in more details on principles, how the electrons are moving in molecules and what is going on. Okay, and some of you have prompted me that there is a duality, that photons and electrons share properties of particle and a wave. So in order to be able to tell something about electrons on more quantitatively, we need to be able to speak about waves and wave processes on a math language. So we need to recall, develop, or find out how to deal with waves. They're more challenging than regular like point charges or like objects in our macroscopic, typical objects in macroscopic world. So we will cover some basic ideas for any wave, and then we will go deeper into electrons. So what is a wave? Just some. Do not hesitate. It's not.
I don't know if that's a good question, but it has like typically an amplitude and like some kind of frequency.
You are speaking about harmonic wave, but the wave doesn't need to be harmonic. So the most typical answer that comes out at this question, everyone is hesitant to speak something out, to be caught on being wrong, and therefore. Any other definitions?
An oscillating form of energy.
One can imagine a wave with constant energy. But something is oscillating. It's good. So, what about throwing Hound in the last episode of Game of Thrones throwing stones at Wichts, and one of the stones was falling down on ice. But if there would be no ice, there would be like water. What happens if stone falls into water?
Ripples.
Huh?
Ripples.
Yes, and they are also waves. And you cannot exactly tell what are their frequency or wavelengths, right? But something wavy in nature is going on, right? Mm-hmm. So we are coming to thinking or defining what it is. So some of you told the word oscillation, so it is something developing in time, but also it is something distributed in space. So a wave is something that connects space and time. So one of the definitions, or one of the possible ways to speak about waves by several options. I'll try first here on the screen, maybe it will work better. So you see, if we do have some distribution in space, but think about one-dimensional, Do you see it well? Maybe a little bit this finger all the time. And then after some delay of time, we have the function with the same symbol, but the structure will be repeated at some elongation. So t is time and x is position. So same function. So if you have some crazy distribution in space, and after some time it travels and reproduces the same shape, but at different location. So perturbation of something, we are not yet specific. For example, it could be surface of whatever, lake or swimming pool, and the shape is repeated. This is a good definition of wave on mathematical language. So a function that is repeated after some times in the same shape and at a little offset. So if we accept this type of mathematical definition, how would you discriminate between waves traveling in different directions? Like wave can go left or right?
Change the minus to a plus on the
Yes,
sign.
yes. Yeah. So you can have left and right wave, or forward and backward. Good, good. Now you are certified experts in waves. But we have a few other things for you. When you did right, the easiest thing while talking to the waves is something periodic, something harmonic, which is much easier than waves of arbitrary shapes. And in most of applications, one speaks of harmonic waves. If you are not dealing with explosives, shock waves, which are exotic. To the majority of the waves that we consider will be some sort of periodic or harmonic. So then you design a function that will repeat itself if you are offset either in space or in time. Maybe you can even tell it as a definition. So periodically repeats itself. Now it needs to be tick in space and time. Well, if it will be too hard, I will go to the old technology. And periodic means repeating the same shape. One of the examples is trigonometric functions, right? I do not have a language to explain it. It seems evident, but we need to pronounce it together. So, like, if you draw, some of you told that there is an amplitude, frequency, and if it is a wave periodic in space, then one can measure if it is periodic, then there is a period. Distance between repeating units. How would you call it? Did I roll it? No. Okay. So if there is a length of wave, so for this lambda, what would we call?
Wavelength.
Yes. If something repeats yeah, we shouldn't dance here. But I don't know, there is no fifth floor, but maybe there are some
Perturbation.
perturbations, or I don't know, maybe martial arts class.
Big birds.
So, if it is periodic in time, then between the same instances, like the harmonic function comes to the same amplitude, we can stopwatch time between these periodic events, and then you can call it. You can call it
A period.
yes. But then we can stick it, this harmonic function with two types of argument into the same functional form as we collectively designed as a group of intellectual activity people on the last slide. So function repeats itself if there is an offset in time and in space. So we set up this function as a sign of argument that shows us shift in space and thing that gives us shift in time. Right now, we did a very important thing, but intellectually it doesn't go beyond high school program. We will develop a little bit further, I promise. So, what is the goal? Well, I know the goal is for me to finish the class and get more free time, for you to get grade and also get more free time. But locally, right now, if we need mathematical laws for motion of electrons, and before we go into this, we need some principles to describing wave motion. What can we always tell? Hey, our electron is cosine. I'm not sure if you can tell it in public. Even if sometimes it could be correct in very limited cases, but you cannot do this way. It will be very non-general. So typically, the wave is a solution, but one needs something that generates them. A wave generator in mathematical sense. So
Function.
Huh?
Function.
No, function is a wave, but not generating function. It's a different chapter. Typically, the functions come out of solutions of differential equations. So we need some equation by solving which we will get a wave type of solution. We are not in math department. We are not in math class, so we should go relatively easy without too much stress, but some minimal effort cannot be avoided. So we are not going to Dirac, but we are going to guess an equation that will generate waves as its solution. Objections? Motivation is clear? Okay, so we will guess such equation by, and we are not going to solve it ourselves for most of the cases, but we will not make the rigorous proof, but we will try to make it clear case. Come to such level that no one objects or no one tells that I suspect it is wrong. So, in order to come up with an idea of what could be the, let me write it down. So the goal is equation. And if it will be equation to generate waves, it will be wave equation. So in order to come up with this idea, we will do two mathematical experiments. So one mathematical experiment, I know you didn't came here to study math, but it is so simple and enjoyable that maybe you will forgive. So what if two waves are colliding? What is going on? What do you expect to happen?
One of two things, constructive or destructive processes.
Yes, yes, yes. Yeah, that's so correct that even Bohr. I was expecting. I was expecting some wrong answers that would sound exciting, like a wave would scatter from each other and go in the opposite direction. So, suppose we have localized waves, not as a infinite periodic function, but like short wave packet train. Two of them collide, and what will happen after they pass? Will they change or not? So some of you prompt that they will not change, and it is again so right boring. There is in basic wave processes there is a well-believed principle of superposition, which means if you add together several waves, they just are constructively or destructively added, but they do not affect each other. So there are no nonlinear phenomena. It's all linear. And we are going to make this experiment by adding together two waves that travel opposite directions, by having different sign in their arguments. How would we do it? Mathematically. How would we add two cosines?
Use a trig identity.
Mm-hmm. Do you remember?
I
I don't. I have a cheat sheet, but I
don't know.
Let me guess and then look into the cheat sheet. But maybe some of you were studying well in other classes and can guess it well. So,
It's like the cosine of the first one minus the second one or something. I don't remember.
like, I'm so lazy that I would die to rewrite this cosine and all these arguments. Let's write down as C sine alpha. I'm not guilty. It's a technology. If it will fail, I will write here, but it's so impressive to. Beta plus cosine alpha minus beta. Where this alpha and beta are those time and space.
I could pull out my phone.
Dang it. I have it. It's at home.
If I were doing the math for him right now, it'd be a cheat sheet I could just look at.
Probably one can recall equations for those expressions separately and then add them together. So I will do my best guess. Alpha plus beta could be. And later, if you need it in class, I do have algorithm how to rederive these equations. I cannot recall anything, but I know how to rederive it within 10 minutes, which we do not have now. Therefore, I'm guessing. So cosine alpha times cosine beta plus sine alpha times sine beta. And cosine alpha minus beta will be cosine alpha cosine beta minus sine alpha sine beta. And if I'm not wrong, by adding these two together, one will get the addition of two cosines on the left. Then, and on the right, these two terms will repeat because they are the same. So 2 cosine alpha cosine beta. And these two cancel because they have opposite sign. Does it sound legitimate to you?
Well, I found the correct one.
How wrong am I?
Well, it should be, let's see, 2 times the cosine of, let's see, wait, how are you starting this? Because the alpha and beta are different here, I think, between what you got and what they've got.
Well,
but yeah, that's more or less correct, because it's the cosine alpha plus cosine beta is 2 cosine alpha plus beta over 2 times the cosine alpha minus beta over 2. At least that's what this
So
picture is saying.
what I'm
Oh, it's a habit.
worrying about, are there here both cosines or there are two different functions?
They're definitely both cosines.
Okay, so if you find any mistakes in the lecture, write it down, bring it, and you will get extra credit. So let's put it in constructive way. Okay, what do I have in my? Either I was wrong by preparing cheat sheet, or I was well, it was consistent. Either mistake here and there, or correct here and there. So if we plug into this shorthand notation our two colliding waves, instead of summation of two waves, one will get product of two waves. So cosine of this space part and cosine of this time part. What does it mean? How do we interpret it? Now we are coming again back into high school program in science. Like the wave in this form was a running wave. This maximum and minimum were traveling one way and another way. But when they collide, we do not have difference, we have product, which means we do have this time, the space-dependent part, but the time-dependent part serves as its amplitude. So the same shape, just changing, lower or higher, right? So we have the shape corresponding to the spatial part, but at next time it will be a little lower amplitude, then a little lower amplitude, and then it will get negative amplitude. Right? No objections. This will be our f capital of x and t, and this will be x. So you will see that, well, here 0 was 0. You will see that there are points that you have always 0 amplitude, and there will be points where the amplitude is changing. So does this wave travel anywhere? Well, can we tell that this wave is can we name it as traveling wave? It's not the best name because it looks like standing somewhere. If it is standing, then how do we call this wave?
Standing wave.
Yes, okay. Good. What else? I want to be lazy. I don't mind to be. So writing long equations is always boring. Why don't we call the spatial part as x capital and time resolved part as t capital? Just if I have another attack of laziness, I will use these notations instead of writing long equations. So this will be x capital, this will be t. Good. How are we doing this time? I'm not yet on the. Okay, good. So same thing we already covered. So by looking different fractions of period, we will get different amplitudes, and there are other points. Excellent. We are done with mathematical experiment number 1. Who we are and what we are doing. We are trying to come up with well-argumented, although not rigorous, derivation of an equation that will generate waves. And we will come to this equation by making 2 numerical experiments. First was to explore superposition that sets up a bridge between traveling waves and standing waves. And second experiment will be to practice derivatives. Why? Because differential equations always have derivatives. We have a big hope that derivatives help us to solve everything. Its answer. No, I should hide it. Probably I will do something here and then open the cheat sheet. Yes, I do actually. Okay, so we are going to practice. Well, I'm going to practice. You probably will just glance and even have no notes or no report. But you're always welcome to take notes. So we are going to practice derivatives over time and space of this standing wave. And there are expectations that we will come up with some really good, I just don't want to block the view, really helpful conclusions. So our function is product of space and time part. And we are going to practice 4 derivatives. First derivative over space, second derivative over space, first derivative over time, second derivative over time. And when we complete this exercise, or when I complete this exercise, should I invite someone to the board, or let's have an easy Friday? Next time. It's too easy for you guys. You can do something more complicated. I'll do easy task myself. So after we are done with these 4 derivatives, we look on them and we will have an insight. We will immediately figure out the differential equation that will generate functions, wave solutions. So first derivative over x. So the time dependent part is not affected, so this derivative will be applied only to the part that depends on space. T, and here we have d dt of cosine 2 pi x over 1. What do we do if the argument doesn't coincide with variable? I think we place it on front, right? And what is the derivative of cosine? Plus or minus?
Negative.
Huh?
Minus.
Negative. I'm with you. Yes. Again, so correct. So we repeat this t capital. We migrate this 2 pi over lambda to the front. And then we have minus sine of the same argument, 2 pi x over lambda. No errors. Finding errors gives you extra credit. Now let's do the second derivative. d2 dx squared, which means we repeat things that are not space dependent. 2 pi lambda t capital, which is function of t, and then we do d dx of minus sine 2 pi x over lambda. What is the derivative of sine? Sine is cosine. Plus or minus?
Plus.
Well,
In this case.
Plus. We keep the minus from our previous history. And again, this factor will come up front as once again, right? So we do have pi over lambda squared. We have time-dependent part, and we have minus cosine 2 pi x over lambda. No errors detected? Not yet. I'll do a lot of errors, I promise you, even involuntarily. Will you see this line? So if I read up until this line, everyone will see, right? Okay, probably I do it. So this was space. Now we need to focus on time. Time. What is time? Okay, we still have about 15 something. So dt of f. Now we will have spatial part untouched, and we apply ddt to the this t capital function, which depends on time. Cosine 2 pi time divided by period. I'm not good in notations. Probably we should call this tau to be different from the function. Okay, and we practice the same thing. The factor comes up front, 2 pi over tau times spatial part, and then we do have minus sine of this 2 pi t divided by period. Right? Very pure analogy. Now we practice second derivative, dt squared. So we just apply second derivative to this expression, which means whatever we got there can be kept in front. So it is not a big discovery, but see how nice. If you apply derivative over second variable, the part that depends on first variable stays unchanged. And it is connected for all problems that are linear in nature. It's this principles of superposition and separation of variables will come up onto your radar if it didn't yet. dt of what? Of minus sine 2 pi t over tau. So derivative of sine is cosine, and we keep the minus sign. So, and we also have this thing once again. So 2 pi over lambda squared x cosine 2 pi t over period. Let's look on these two expressions. So we have done torture of our young brains for technical issues, and now we will play highly intellectual observators. So what do you observe if you look on these two expressions? How different or how close are they from each other? What is common and what is different? Okay, easier thing. What is common? Do not hesitate. It's anything you tell can work only towards your benefits. There is no punishment for anything.
Negative cosine.
Yes, so the non-trivial functional form is
Double checking quick too. Is
Ah.
that supposed to be a tau?
tau.
Instead of lambda on the far left of that bottom equation.
Yes, you are correct. Plus 1 point. I need to learn your names and make a little table.
I don't think that's much of a correction. I just wanted to make sure.
Good, thank you. Maybe it is too early to compare. Maybe we want to plug in explicit values for this t and x. So what if we replace t with cosine 2 pi t divided by tau, and we replace x with cosine 2 pi x divided by lambda. Is it easier to compare now? So you see that everything starting from this point is exactly the same. You do? So we have some crazy constants in front different, but in fact, second derivative over time and second derivative over space bring up the same answer. This is really great observation. So right now you come to the point of truth where you guys will derive an equation for that will generate waves. So we need to record that they are equal to each other. So if we multiply each side by appropriate factor to get rid of, like if you multiply both sides of this equation by tau over 2 pi squared, then it will disappear on this part. And if you multiply this equation by lambda over 2 pi squared, it will disappear from the right side, correct? And then we can establish the equality. So please try to write it down in your notebooks and see, and then correct me if I will do it in the wrong way. Lambda over 2 pi squared times d2 dx squared of f equals to tau divided by 2 pi squared d2 over dt squared of f. This one appears from here, this one appears from there. Objections? Do you have, well, it is not the last one, we can simplify it a little bit more, but would you agree that it makes sense? Good. Probably it will not work. In this place. Do I have your permission to erase everything? Good. Maybe everything except this last equation. So we can cancel 2 pi here and there because same power, same like denominator, and then we can divide both equations by tau squared. So divide pi tau squared. Then you have lambda over tau squared d2 dx squared d2 dt squared xt. By the way, it's already time to celebrate. You do have an equation that will generate waves. We just work on little improvements to have it looking nice. What is the dimension of wavelengths?
Distance.
Yes,
Meters.
like meters, feet, miles, parsecs. Oh, what's the units of period?
1/2 seconds.
Period, not frequency, period.
Seconds per meter.
Period.
Just time, like seconds.
Yes,
Oh,
time.
seconds.
Seconds. Then this one is, how will you say position, coordinate, distance. Distance, and this time. What is distance over time, based on your, probably it's not high school, it's middle school, or just common sense. Like miles per hour. Yes. Velocity. Velocity of whom? Or velocity of what?
The wave.
Yes. So v squared, velocity of wave, times second derivative over space equals second derivative over time. So it's wave equation. So it would be too much and too demanding for us to go into solutions of this equation right now. I'm just switching back to the slide. Slide. More. Up. But if you would have enough time or enough money to hire a professional mathematician, solution of this wave equation always give waves. Not only cosine waves, not only waves of a given frequency or given period. It gives more general waves, including wave packets, superpositions of several waves, traveling waves, but this is a big record in our intellectual development. The important feature of any object where one can see waves is that unlikely like pieces of whatever wood, iron in our macroscopic everyday intuition, these objects have infinite number of degrees of freedom because you need to see elongation at each point of space. Like if it is surface of water, it elongates a little bit from equilibrium up and down. The simplest wave is the string on musical instrument, like violin or guitar. So it is able to show complicated shapes. Although typically it shows very simple harmonic, but generally wave equation can give some exotic shapes. Good. We are very good. You are good. So what's the connection to electrons? And I want to learn how to time manage. Okay, 5 minutes. Is there a person in the room who never watched TV? Okay, we all are in modern civilization. Is there a person in the room who never watched flat screen TV? Okay. Now let's formulate other. Did any of you watched non-flat screen TV? Good, good. So how does it work? I mean, not as users, but if you travel in time 1,000 years backwards and you want to redesign the TV.
Cathode ray tubes.
So first, it is a like a big glass tube with the screen is front area. Second, there is vacuum inside, and third, there is a gun, electron gun, the device that emit electrons, and they approach the screen. When the electrons approach the screen, it flashes because of scintillation. And then there is additional technology how to direct it to different points on the screen and how to change intensity. But basically, it's flashes or non-flashes at different points, and then gives us a movie or whatever. So gun, and then there are ways to engage, and then there are flashes. Good. Now, double slit experiment. What is it?
Sending waves through, or like a light beam through like a double slit, and it produces like this line of
Yes.
dots.
Yes. You are talking about double slit experiment for light waves, like interferometry. But one can make the same double slit experiment for electron. If you have technology to redesign the old-fashioned TV device, and instead of allowing this electron ray to hit any point, you will make a screen inside that will and make two holes or two slits there. Then intuitively one would expect that electrons will go one way and flashes in one position, and if there is a second hole, it will flash in another position. But if one makes this experiment very carefully in dark room, one will observe that something happens in between, and this will be a manifestation of wave nature of electron. What are atoms? I know it's a bit of changing the gear, but you know, before 20th century, 19th century, there were models. No one was objecting positive and negative charges, but there was a raising pi model of atom. So it's like homogeneous positive charge with electrons like raisins sticked around, well, inside. But it was given wrong results for many experiments. And historically, the Bohr model told that it was the first one who reproduced the spectra, the discrete nature of spectrum. And raise hands if you never heard about Bohr model. Okay, you've heard about it. So it was an idea that electrons cannot stand in a fixed space. They always move. And they move on orbits. And they move on orbits only with selected values of velocity, distance, or better say angular momentum. Very discrete values. We are going to look on this aspect once again and connect it with our knowledge of the wave equation. So here is. So we are coming to the end of the time for today, but you can think about Bohr models, about some waves going in circular orbitals, and what is important that these waves of something come to the same phase upon making a full circle. Waves of something make a full circle and come to the same phase. And if we do not have the integer number of cycles, then something crazy is happening. So those are good Bohr orbitals, and those are bad orbitals. See, you cannot associate, while looking on these images, you can speak, this is like p orbital, this is maybe like F orbital, something like this, but here you can associate this shape with anything. If there are no integer number of pure rotations of some object of unknown nature, then one gets a mess. This is something to think about over the weekend. Thank you much for coming, and looking forward to see you on Monday, 11 at the same spot.